Good morning to all. So, to take you to deep learning or to go to deep learning, let me quickly spend a little time on backpropagation in neural networks. I tentatively plan for 10 to 15 minutes to spend on the neural networks. I will not go into the details, full details of backpropagation. I assume that you might have seen or studied sometime somewhere and you know partial details or you know full details. I will only try to bring in the notation and want to have a connectivity for the next discussion on convolutional neural networks. I would like to bring in some insights while I discuss on convolutional neural networks from the neural networks. So, that is the reason why I am discussing the neural networks backpropagation a little bit. So, I will put 15 minutes for it. After that 15 minutes I would like to spend on what is the need of what is this convolutional neural networks. Okay, what is the need of when you have already neural networks, why do you need some other learning method like convolutional neural network. Okay, another half an hour tentatively I will put on discussing what convolutional neural networks are and how they can be trained or how they can be applied in basic classification task. So, this is the tentative timeline of my discussion. So, let us anyway get into the feed forward neural network. So, as in the previous talk you have seen, the notation of neural network may be slightly different, but I hope you will be able to understand. So, what is that I am drawing here? So, I am putting some zeros. What are these things? Neurons. Okay, you can consider them as neurons or nodes. Okay, and we have the interconnections in a neural network. How will be the interconnection in a feed forward neural network? Input to hidden layer neurons, all input neurons to all hidden layer neurons. Okay, so this is that's why the name has come as feed forward neural network. Okay, so this is feed forward neural network. Fine, we are feeding all neurons to the next layer. So, all will have connections. So, if I do like that, if I have, say for example, I will bring in some notation, xi is the input here, okay, and say x1, x1, x2 and so on up to xd are inputs. So, essentially the vector x is the input. What is this vector x? In a practical scenario, when we want to when we want to put a sample as input to a neural network, what is the text? Input feature vector of what? Of the given data. Given data is not very clear. Of given data sample. Okay, can you give an example? Say if I want to do digit classification, let us take the simpler example or known example, digit classification, okay, 3, 5, 1, 2 and so on. We give a 2D matrix of the image of the digit as input to the neural network. That is what we want to do, and the output what we expect is, see if I give as 3 as input here, what I expect at the output? Output how many neurons will be there? For a digit classification from 0 to 9 digits, how many output classes will be there? 10 classes will be there. So, 10 output neurons will be there. So, how do I decide the number of output neurons is based on the number of classes, right? And how many input neurons should I put for this classification problem? So, assume that this is 20 cross 20 image. Okay, I have an image of handwritten, you know, we have the handwritten digits, right? I take a small image of it. That image is 20 cross 20 pixels. Okay, I want to put directly that image in one dimension. I will just put the raster scan of that image and put in one dimension as a vector to the input. So, how many neurons has to be there at the input? 400 cross 1. So, essentially 400 cross 1 or whatever, this depends upon what? The input number of neurons depends upon the number of features. Okay, this depends upon the number of features I have for the sample, for each sample. Okay, and then this the output depends upon the number of classes. And how many, say assume that, say I just for generality, I assume that there are D neurons, input neurons, okay, and then there are H hidden neurons, and then there are C output neurons. Okay, this is the the generality. I am giving some symbols for it. So now how many interconnections will be there? So in a feed forward neural network, how many interconnections from this input layer to the hidden layer? D by H, of course, we can call D by H, it is D cross H or D into H, okay, DH essentially. So if I have 400 and 100 here, I will be having 4 into 10 power 4 interconnections. What do I mean by interconnections? These interconnections are what? What does these interconnection carry? Weights. Okay, so Wji will connect, for example, any of these, if I consider this as Wji in general, it connects Xi to Yj. Okay, let it be, I have given a general notation, but we can, Yj can be 1, 2 and so on. Okay, similarly Xi can be X1, X2, anything. So the weight Wji connects the ith input neuron to the jth output or hidden neuron, jth hidden neuron. Is this fine? And then this, how many you said D cross H? This is the, if I want to represent as a matrix W1, okay, one matrix, W1 matrix, whose elements are Wji, okay, then how many elements this matrix has? How many elements, what is the dimension of this matrix W1? D cross H matrix. Is this D cross H? So Wji I have put. So essentially what I am doing, this is H cross D matrix. Okay, because see, if I can put in either way, but I have given this side and J I have given to this side. So if essentially why I have put in this way is, see, if I want to write in vector form, how do I want to write? What is this vector y, y1, y2, y3 all together? Okay, all hidden on neuron outputs is y. Okay, and then this W matrix I will try to use, and then what I have input as x, W into x essentially, okay, is supposed to give me y with, if I consider an activation function f, this is what is the relation between y and x. Is this clear? Okay, so only thing here is I have not considered explicitly bias. Okay, of course you can absorb the bias in the x vector as you have seen in the previous lectures. Okay, so we are not explicitly putting it. Of course it is needed in general. Okay, bias is also there in general, but we are not explicitly highlighting or putting that. Okay, so that's the reason we usually consider its dimension to be H cross D. Okay, is this fine? Right? So now each of the input neurons are connected to the hidden neurons, fine. Okay, and then each of the hidden neurons are connected to output neurons. Now how many interconnections do you will you have here? Will we have here? Wkj I denote, okay, the matrix W2 here, okay, with elements Wkj, and how many interconnections do we have? C cross H, very good, and the matrix W2 will be C cross H. Okay, like we have made the J again this side, okay, not on that side, fine. J comes to the, in some sense it is on the rows, not on the columns, okay, fine. So now this is same, if I want to create output O, if I consider here as the output, okay, O is equal to what? In this similar fashion I can write O as what? O as W2 into G, of course I can consider G, or F itself I can consider, assuming that the activation functions are same. So W2 into Y, very good, okay, into Y, fine. So what is now there are a few questions quickly we will ask, and then we will move on to the idea on back propagation. Okay, so why do we need nonlinearity? Say if I am writing an activation function and so on. Okay, previously you have seen in a binary classification problem, okay, where you want to classify the samples of one class and other class. Okay, finally you ended up with a linear line, W transpose x plus b equal to 0. Okay, and this side, one side is positive, other side is negative, and so on. Okay, so there is no nonlinearity here, and the model essentially is trying to find out W and B, and hence Okay, a neuron typically does not need a nonlinearity. But why do we need nonlinearity in a neural network? Why do we need nonlinearity? Quick answer? We don't need nonlinearity? Yeah, we need. Why do we need? Huh? Okay, very good. One answer is decision boundaries are complex. So I assume in some way. Okay, your answer I assume that. Okay, the samples are like this. Okay, I can draw any crazy location of samples. Once I make this, this decision boundary can also be like this. So for this to bring in, you have to have nonlinearity somewhere. Okay, and you need to have it. Very good. Any other answers? XR problem, for example, doesn't have nonlinear decision boundaries. Two linear decision boundaries it has. Okay. The one thing is, if I put all of them linear, finally what will boil down to? After a couple of linear operations, okay, I will keep writing one linear operation, on the top of it another linear operation, and the top of it other linear operation. Okay, what will finally boil down to the relation between input and output? Linear. Will be a linear operation, nothing else. So I can't have the complete, if I knock off all non-linearities, I can only get linear decision boundaries. Okay, and that too a single linear decision boundary, which will not enable us to essentially bring in the non-linear decision boundaries or non-linearly separable samples to separate. Okay, what do we mean by non-linearly separable samples? Are not linearly separable samples are like XR problem. Okay, which are not separated by a linear line. Okay, so fine. So given all this, now we have some relation between output and the, see, if I want to relate now output and the input, I can use these two together. Fine. Now the question is, as we discussed, what is learning happening here? What are to be learnt here? What do we want to learn here? It's fine. You have actually input features, okay, presented, output class values you are getting, okay, and then W somehow I initialize, assume that I initialize randomly, and then what do we want to learn here? Why do we want to learn weights? Why do we want to learn weights? Okay, if I don't learn it, okay, then if I give 3 here, do you expect that the for third neuron, okay, which is supposed to be high, say that class 3 should be 1 for third neuron, okay, ideally, and other neurons should be giving 0, 0, okay, the 0, 1, 2, 3, 4, 5 and so on. Okay, this has to give high value compared to other values in the output. Okay, that is how it should be if it is well trained. Okay, if I give 3 as input, it has to give high value to the third neuron. If I give 2 as input, it has to give high value to the second, okay, the third neuron here. Okay, if I give 0 as input, first neuron it has to give high value. If I randomly initialize and start using it, will that happen? Will that give a high value for a 0? If I give 0 as input here, do you expect that the 0th neuron always get a high value? It won't happen. So I have to learn these weights and biases such that for each of the correct some class sample, I will get the corresponding label as high value here, or corresponding probability or corresponding output as high value compared to other outputs. Okay? So for that reason learning is necessary. So the predicted values of the outputs has to match with the target values of the outputs, right? So these are assumed that the target values of the outputs, that is given by T. Okay, I am just denoting this vector, okay, output vector as T. Now given all this, so what, how, see, if they may not match, as we said, if we don't train it, but to train it we need some, what do we need? If we want to train it, what do we need? We need loss function. So what is the loss function? Say if I randomly initialize and give a some input, okay, keep giving inputs, I will not get the expected output. What is the discrepancy between the actual output, okay, target output I want to get, and the obtained output by the network? This discrepancy over all samples, in fact I am not considering all samples, currently we are just considering one sample, okay, all samples, this discrepancy is the cost function. Okay, fine. Now the question is what this cost function is function of? what is that I want to do from this cost function? From this cost function, what do we want to do? What do we want to do from this cost function? We want to minimize loss. Okay, with respect to what? With respect to all the weight parameters. So W1 and W2. When I write W1, W2, these are matrices. Okay, explicitly writing dou of Wij, sorry, Ji and Wjk. Okay, Kj. Okay, with respect to all elements of weights, okay, I want to minimize this. Where are this Wji, Wkj and so on in this loss function? They have to be this side also somewhere, right? Where are they? In O. Okay, O if I want to expand, it is in fact W2 times Y. Okay, I can write like this. Of course, I can also write this as W2 Y, oh sorry, another f of W1 x. Okay, of course, I can also write in this way. I have left the biases and so on separately. We assume that everything is absorbed in this. Okay, so now if I W1 and W2. Okay, so now what we want to do is we want to learn the weights such that, how should we want to learn the weights? Such that the error, discrepancy between the target values and the predicted values output of the network. Where is the network here? This itself is the network. Okay, network means it doesn't appear as network there, it is just a function. Okay, so the output of this minus the target values has to be as minimum as possible, or they have to be as close as possible. Fine. So now to do that, what should we do? With respect, we should learn these weights such that this is less. So what should we do now? What is the next step? We have to do back propagation, or what is that back propagation means? Adjusting the weights. So essentially what I want to do is dou J by dou W2 for example. First I want to adjust these weights, okay, because these weights are near to the loss function. Okay, loss, see this whole network, it may have, as we have seen here, 400 input neurons and 100 output neurons. If we say 40,000 weight elements are here, okay, and then if I put 100 neurons here, 100 neurons and 10 neurons here, 1000 elements are here, weight elements are here. I need to adjust these many weight elements just by what? I need to adjust these many weight elements using what clue? Using the error between the expected output and the actual output. Okay, but see, is that, do you think is it realistic? It is not realistic. So what should I do now? I should look for, say I have presented 3 now and I have got some error, and with that error I want to adjust. Okay, what should I, to adjust these many parameters, what should I look for now? More 3s, okay, more 5s, more 0s and more 1s, is it not? We should have more number of samples such that they generally describe how all zeros are, how all ones are, how all twos are and so on, and also how all ones are different from all zeros, how all ones are different from all fives and so on. Okay, so we need to have large data set usually for training the neural network. Okay, so usually the number of parameters of a neural network, if we consider as whatever the total number of parameters, they are referred to as expressive power of the network. At least 10 times of the number of the parameters of this are the number of samples that are required to train a neural network. Okay, so now I will not get into the back propagation or deep derivative here. Of course, you can directly do derivative with respect to matrix and do that. Okay, I will give the answer. Okay, for this, those who have seen before, try to relate it with something that you have seen. So assume I will tell some hints. See, assume that the I want to write error here. J is okay t minus o or o minus t whole square. See, as we said, we want to find out here dou J by dou W2, okay, Kj. Okay, this is what we want to find, is it not? Each element how much does it vary? Okay, if I change small value in weight, how much does it affect the loss function? That is what I want to see. Okay, after seeing that, what do I do with this value? Dose A by dou W 2 Kj, I assume that I have got. After getting this, what do you think I will do with this? Update what? W2 Kj itself, using this value, how much does it affect the loss function I will take and use this to update the W2 Kj itself, okay, from the previous value to the next value, okay, and then eta times or whatever dose A by dou W Kj. If it influences more, then I have to update it appropriately or more, okay. If it does not influence more, I need not update it, it is fine, okay. So, like that we do that, fine. So, now the question is dose A by dou W Kj I have to get here. So, if I want to see how much the change happens because of this, first I have to see here itself dose A by dou O, okay, because there is an error. See, error is related to output and output is related to what? Okay, W2 anyway, W2 Y. So, output is related to W2 and so on, okay. So, if I want to see the variation of this, I have to see first the variation with respect to this and then I have to see that, fine. So, now dose A by dou O, what is this? Anybody who knows can quickly tell? If I have J equal to T minus O norm, what is dose A by dou O? J I can also write as T minus O transpose into T minus O, okay, and then if I differentiate this x transpose x with respect to x, okay, what is that I get? 2 into T minus 4, very good, okay, I take it, okay, 2 into T minus 4, this I write it as delta O, that, of course, this I write it as delta O, that is fine, okay. So, this I assume that you can probably understand, and from here then what I should do? See, but I have only used the first expression now, I have to use the now second expression and write what? Using the second expression I have to write what now? Okay, dou, I have to write what? Dou O by dou W. While writing here I will play a trick, okay. I will not write for all elements, O itself is a vector because O is O1, O2, O3 up to 10 values are there, 10 outputs, but I will just take only kth one, okay, and then or some one, ith one I will take, okay, or pth one I take, okay, and then jk, wkj I will take, okay. So, only one of the output I am taking, fine, and then one connection I am taking, okay, dou op by dou w kj I am taking. This if I want to write, how much will this value will be? Can anyone tell? Say dou o by dou w kj I want to do. How much will this value will be? This is the relation. How does it depend? See, I will tell intuitively. I am trying to find out, see, O2, okay, with respect to O2 I am trying to find out the differentiation of W, this is 2 1, okay, that is actually 1 1 1 2, okay. So, there is a connection that connects the second neuron here to the first neuron here, okay, but there is a second output here. I want to see if I make a differentiation of dou O by dou W 1 2, that means if I make a change here, how much does it affect this? I want to see how much does it affect. If I make a change in this weight, how much does it affect this output? It will not affect, okay, because 0 it affects, because this is not connected at all. How does it affect? So, this is equal to, ideally say this I will write, this is equal to 0 if what? If where P is not equal to what? P is not equal to, P is the here not equal to, P is not equal to K, okay, because K is this one, okay. If these two are not equal, okay, it is connecting to some other output and I am trying to differentiate with respect to another output, it will be 0, okay, 0 if P is not equal to K, fine. If P equal to K now, what is the answer? If P equal to K, it is second condition. If P is equal to K, what is the answer? Now, assume that I take another connection, okay, which is something like this connection itself, W3, 2 3, okay, this is the connection I take, okay, and what is the output here? Y2 is output, Y3 is output here, and O2 is output, Y3 is the hidden neuron output, okay, and O2 is the output neuron output. So now I want to how much does it influence this? Simply I want to use the direct relation O2 if I want to see only with respect to all y's here. It is, okay, how do I write? So if those who have seen in matrix in element wise writing, O2 if only if I want to write, O2 only if I want to write, how do I write? Kj, yj, j equal to 1 to whatever h. All of these will get added here, right? All these will get added here. So y1 into w21 plus y2 into w22 plus y3 into w23 plus and so on will come. Okay, this is what I will get. Okay, so now of course f is there, activation function is there. Okay, activation function is there. Now leave the activation function for time being. If I O2 by w, so dou O2 by dou y3 if I want to do, what is the answer I get? Or dou O2 by dou yj if I do, what is the answer I get? Dou O2 by dou yj. If I differentiate, see there is a function, if you are not able to see there, okay, the function is OK, okay, in general is summation wkj yj. I am leaving the bias and all, okay, assuming that you can absorb them, j equal to 1 to h, okay, dou OK by dou yj I want to do, okay. What do you think is the answer? I have written very clearly here, okay, the only relation, and what is dou OK by dou yj? Wkj. And in case if there is an activation function, what will happen? That also has to be taken into account. So f activation function, if f is the activation function, somewhere f dash also will come into the picture, okay, f dash of whatever. So if I call this as net k, okay, this value as net k, f dash of net k also comes into the picture, okay, because if I differentiate any say function f of x, if I differentiate, what is the differential of f of x? F dash also will be there, okay, f of x square, if I want to differentiate with respect to x, what do I write? F dash of x square into 2x, okay. So whatever differential I have into f dash, okay. So is this clear? So now just to give you an intuition finally, if p equal to k, what should I get now? It is essentially f dash of net k, okay, that I have written there, into net p here, okay, into what? Y, sorry, not y, I am differentiating with respect to w, right? Oh, here I have differentiated with respect to y. If I differentiate with respect to wkj, what do I get? Y, okay, okay by dou wkj, if I differentiate, what do I get? In this, without f and so on, to make our job simple, yj I get, okay. If I differentiate summation wkj, okay, with respect to the wkj, what I get is yj, right. So now simply this is equal to what? Into yj, that's all. So what finally I will write here, I will just so dou OP by dou wkj, okay, if you want to write, it is 0 if, when it is 0, p not equal to k, and what is the value? It is f dash of net p, okay, net p or net k is same, into yj, okay, otherwise. W I am differentiating, so yj will come here, okay. Is this clear or not? So this I call it as, okay, so this I call it as delta net k, okay, net k or net p same, okay, net k or net p. So I essentially, where k equal to p, right, so it is same, net k or net p, okay. So now what I want to bring in it here is, if I want to write dou j by dou net k here, so essentially what do I have? Okay, see one thing to note here is, what I have written is, I have written the dou j by dou o, I have separated dou j by dou w into two components. One thing is dou j by dou o, okay, and other component is what? Dou j by dou o, which is already computed here, into dou o by dou W2 Kj. Okay. So, whatever I have computed here is what? Second one. Okay. We also have the other component dou J by dou O computed here. So, essentially if I write this, what will happen is this is delta net K, okay, into, so what you have actually delta net K, or what, we will write the whole thing. I will write here, I am erasing and writing, because the last expression I want to use for giving some hint. So, dou J by dou W2 Kj, now if I write together, what will happen? F dash of net K, okay, because K is here, net K will come here, okay, into what? Yj into OK minus Tk. Why I have written OK minus Tk? Because only I am taking the kjth element. I am not taking all elements of O. I am only taking OK. Okay, essentially I am taking K only. Okay. So, this is the final answer I get, right? This answer you can verify yourself with your previous workings or with the detailed lectures. Okay. This I can rewrite as, see how do I rewrite it as delta net K into Yj. Okay, you may ask me what is the advantage of writing, because there are K terms, these two are K terms, this is J term. Okay. If I write like that, what do I interpret this as? See, if I want to adjust Wkj, that is delta Wkj if I want to find, essentially what I am looking at is Yj is what? The corresponding input here. Okay, Yj is the corresponding input here, right? And what is this delta net K? Here, see this value here, if I differentiate this further, O minus T you have got up to here. If I just cross the differentiation of F, see forward operation of this neuron, what it does do? After doing summation and all, it will apply F of, okay, it will apply an activation function. In forward pass, it will apply an activation function. If I want to go back reverse pass, what I am doing here, F dash is coming into picture. So, if I see here for this delta OK, essentially what it is happening this side, okay, not this side, okay, O minus OK minus Tk into F dash net K or net K. If I write net value is what is the value before activation, okay. So, what I am trying to say is the error that it back propagates up to up to this side of the neuron is delta net K, okay. So, that see if I want to update a error of any element, what I should look for is I have to take the input here and take the error here, multiply them to update the element, weight element. This is delta net K into Yj, okay. So, this happens not only at this layer, this happens at all the layers. So, hope you understand the main point I am trying to tell. If you just keep back propagating, you back propagate the error. If you want to update any weight element, then you need to look for what is the input for it and what is the error at this end. Just multiply both of them, you will get the weight update. That is all you need to do. Is this clear? So, because why I have written delta net K here, delta net K is nothing but, okay, O minus T into F dash net K. O minus T is here, F dash net K comes because I am crossing the F in this direction. Okay, if I am going in this direction, F of I will apply. If I come in this direction, that means back propagating, F dash will come. So, delta net K is nothing but, okay, F dash net K, okay, net value means up to here what the value is, into O minus T, that is all. Okay, this is delta net K. So, if I want to update error, if I want to update any weight element, just look what is the error here, okay, from the end, okay, what is the contribution of delta dou J by dou this value, okay, dou net value, and multiply that with respect to the input, that is all, okay. So, if I want to update now any of this element, this I call it as Wji, assume that, okay. I will not derive anything, I want to write delta Wji, That means I want to see dou j by, okay, dou wji is how much, I just want to see. Okay, how do I see that? Can anyone tell me what is the simple way of doing it? Given this discussion, I just want to see now how do I update delta, how do I update this wji using this delta wji, or how do I find delta wji? What are the terms involved in delta wji? There are two terms involved, as I mentioned. Okay, one term will be what? One term will be input. What is input here? X, xj or xi? Xi. So input will be there surely xi. Okay, and then what is the next term? Delta. Yeah, delta net j. Where is net j? Before going here net j you have, and after going here yj you have. Okay, if you cross this you have yj. Okay, if you don't cross it, it is net j. Okay, yj equal to f of net j. So simply you take the gradient here, okay, and then multiply with the input here, you get this weight update. Fine. See, this kind of rule is applicable to any number of layers, not just 2 layers. If you have 100 layer network, there also if you want to update weights, what you need to see? In a 100 layer network, you need to take an error here and you have to pass 100 layers and then update. We can't keep on seeing what the chain rule and so on. What we will see? We try to see what is the error at the rear end and what is the input value, multiply them appropriately and get weight update. That is all. Okay, is this clear? How exactly we get delta net j or dou j by dou net j, that you bother about. Okay, looking at the gradients, chain rule, all those things. Okay, which you might have seen in other places or video lectures. Okay, fine. Okay, so we will stop the discussion here and we will move on to the discussion on the convolution neural networks. Yeah. Any questions so far on this? You can bring down. If you have any questions on this, you can ask. I have enough cluttered the board, but you can ask any question. I will probably put that separately. So what I would suggest is, if you want to understand and apply the neural networks, you take a 2-layer network, okay, put all the forward pass relations and write the output, how is it related to y, x and so on, okay, and then write the error, write the derivatives, okay, from j to o to net value here, net value to y value here, y value to net value here, net value to x value here. Okay. So derive yourself those derivatives and then put together to see these things, or put together to understand or exactly get the details. Okay, fine. Okay. So let us see what is the need of neural networks. So convolution neural networks. See, what do you think is any limitation of neural networks? That is the question now. Anyway, as we discussed, if you want to perform any automated task, we need to first start with some pre-processing, feature extraction and classification. So we have seen also that features are different for different kind of data, okay, and often it is not very easy to take the direct raw samples, either pixels or the signal values or any data values, okay, let it be binary or whatever, any values directly, raw data itself as features. We need to, usually if you want to give it to any neural network, any classifier, we need to first extract some handcrafted features, then give them for classification. Okay. So these we have seen, and computer vision field has evolved a lot in terms of what features are good to represent an image or objects in images. Okay, and then one of the very successful feature extractor is histogram of orientation gradients, which will take the gradients of an image and take the gradient angles and make a bins of them or histogram of them to represent the object shape. Okay. So for humans, all angles will be on 90 degrees, for example, if we consider as 0 degrees. So then you will have actually the human separately represented by dominated 90 degrees angles of the shape, and say if it is a horse, for example, it is dominated by 0 degrees, something like that. So that's widely used in computer vision, and this kind of handcrafted features are very much important if you want to perform classification by conventional machine learning methods. Let it be neural network, let it be support vector machine or any other method. Okay. But the difficulty is for each data type you need, or each application also demands different kinds of features. Same features that I extract for a face detection may not work for a fish and non-fish classification, other fish classification. So what kind of features are more important is has been a important question. One observation in that lines is the features are extracted through convolution operation. As we mentioned in the previous discussion, say if I want to highlight the edges, what kind of filter do I use? I use an edge filter which looks like 1 1 1 minus 1 minus 1 kind of thing and convolve, and then I highlight edges. If I want to highlight corner points, then I design a filter like a corner which looks say 8 in the middle, okay, and minus 1 minus 1 minus 1 minus 1 in the all surrounding 3 cross 3, then that looks like a corner, right. So if I visualize it 8 in the peak and then minus 1s in the surrounding, that if I convolve with any object, any image, I see that the corners gets highlighted. Okay. So for face, as we discussed, face filters, okay, can be there. So like that, if I design appropriate filter, I get better features enhanced. But the question now is, there is one parallel thought or parallel line of methods that are on investigating on feature extraction, and with filtering also you can do feature extraction with different filters, you can extract different features. On the other side, learning methods has evolved to learn directly for classification. If I give you features, we will be able to put into the separate classes or find out the regression value and so on. So on one side, learning methods have evolved to map the input output relationship, okay, if I give features to the output. On the other side, what kind of features are we looking for is an important question, and filtering also is known to be a good answer for it. The question, the subsequent developments has looked at, can we have a combination of them? Can we have these filters itself, can they be learned in a process, and then can we extract features also without hand grafting the features or without picking up some features, and also train the feature extraction stage as well as classification stage? The answer to this is convolution neural networks. Okay. So this is one importance of convolution neural networks. The other thing is, see, when I give any image to the network, what do? I will make one dimensional vector and give it to the network. When I make it one dimensional, there will be some problems. Okay, we will see that. So these details I am skipping now. This is what actually we have derived just now. Okay, this is the whole expressions. Okay, and then when you see finally what will happen, the weight update here is equal to the delta net here and the input value here. Okay. So in vector form also it nicely fits in. Similarly, even in next layer, okay, if you go also, the output input vector here, okay, multiplied by the error here will put into the delta here. Okay. So you can see that later. And what essentially neural networks learns in this process is, if you have an input sample here and if you have output variables here, if you see mapping from input to the output directly, then if you bring in this any W that it learns to give a high response for a particular class, that W itself looks like a object of that class. Say for example, if I give a car image here and if I am getting a with very well trained neural network, I am getting high value for a car here. If I see the weights connecting all inputs to the class of car here, okay, that weights, if I put those weights, okay, in 2 dimensions, that itself also looks like a car. Okay. So what essentially it is extracting is that W filter. Okay, if I consider even W as a filter, that W filter that matches very well with the all input samples. Okay. So if I have all cars, assume that if I have a some average or unique representation of all cars, okay, that itself is what is being learnt as W here. Okay, if I want to see as mapping between input and output. So now the question is, how do we learn that such filter directly? Okay, without this is of course learnt in even in feed forward neural network or even in conventional neural network, but the problem is the ability of it is limited because of few things. and how do we do better is the question. So, one more problem for developing deep neural networks is, as we have seen, when we back propagate, what will happen? At each stage you will have one f dash, because each layer, if when you cross, there will be one f dash added here, another layer if you cross, one more f dash added here, okay, added multiplied here, okay. So, weight update, if you want to see after 10 layers, okay, it is function of all these many f dashes, okay. Weight update after 4 layers, if you want to see, these many f dash terms will be there along with other terms, okay. Each f dash value, if you consider sigmoid activation function, okay, f dash value is in sigmoid is in the range 0 to 1 and f dash of sigmoid is in the range 0 to 0.5 only, okay. If that is the case, what will happen? These many, each of them multiplied by 0.5, 0.5, 0.5 because of f dash in 10 layers, then what will happen? The weight update dou z by dou w itself will be very small. So, for that, usual answer that people have brought in is use the activation function called ReLU. What is the ReLU activation function? Rectified linear unit activation function. What it does is, so instead of the sigmoid activation function, for f of net value sigmoid activation function, what it does is, it tries to map the input net values, okay, to something like this, okay. So, essentially it will try to map 0 to 1 here, then this is half here, okay. This is what it is trying to map, net value to f of net value. Whereas sigmoid activation function, what it does is, this will have a small gradients, sigmoid activation function what it has is something like this, okay. Sorry, this is ReLU activation function. How it has is, net value it will map to, okay, net value itself on the positive side, okay, on the negative side it puts to 0. Because of this, what will happen? The gradient in negative side is 0, positive side is 1. So, this because of this, this f dash does not die down. So, this is addressed, but the problem is, if we want to consider feed forward neural network and give a 2-dimensional input to the feed forward neural network, if you shift the image or the object by a small amount, then what will happen? Previously where you have learnt for A, okay, in other neurons is not there as A now, okay. So, previously whatever the neuron supposed to predict A now will not predict A, okay. So, if with small shifts, the input you give to instead of one neuron to some other neuron at all, completely different neuron, okay. So, this will bring in a difficulty in terms of learning, and even if rotate and so on, okay, what will happen? Okay, whichever you have learnt all A's with having high value for first 10 neurons, okay. Now, after rotating, what will happen? They may be in next 10 neurons. So, if you bring 2 dimension to 1 dimension, the whatever you have learnt for some neurons will appear in some other neuron in testing, so they will fail. So, what we need to do is, we need to have a method that directly takes 2-dimensional input. So, all these are being addressed by convolution neural networks. So, what convolution neural networks does is to represent the, if you have image, first let us extract some features in 2 dimension itself. For extracting features in 2 dimensions, what do we know? What is the good operation to extract features in 2 dimensions? Filtering, convolution. So, apply some convolution and get features, and these features can I assimilate together and make better features, high level features. Then let us put one more layer of convolution and see can we assimilate better, okay, and then put one more layer of convolution, can we assimilate even better. So, what it tries to does is, it tries to extract the features layer by layer, low level features to high level features directly in 2 dimension or whatever the dimension of the data itself. If I have a RGB image, it is 3 dimensional, so x, y and RGB, okay. So, it can be directly given to a convolution neural network. No, there is no need to bring it to 1 dimension or 2 dimensions. So, any data let us try to bring in its own dimension and try to find out the features in that dimension itself through convolution operation, and can we assimilate them in a layered manner and get better features and classification as well. That is what is being addressed by convolution, done by convolution neural networks. I will skip the very basic details. The layer of the structure of convolution neural network looks like this. As I mentioned, the greatness or the famous reason for convolution neural networks being famous is it is very simple, okay. It only has 2 building blocks, ideally speaking, okay. One is convolution layer, as we mentioned, perform convolution, that is all. Only the question is, which mask or which filter to use for convolution. If I want to find edges, I have to pick edge filter. But if I want to perform say cat, dog, person and so on 1000 class classification, which filters to use is a big question. So, it is answered by the learning method. I will learn the filters itself. Okay, what 3 cross 3 filter should I use is also being learnt. Okay. So, that is the convolution layer is first layer, and I can bring what how many features should I extract. Say edges are only features I want to describe an object, corners also I need, corners are and edges only these two features I need. I also need texture features, I also need few other features. So, bring several feature maps, not just one feature map. Okay. So, each filter here will give one feature map. I can get actually 6 feature filters. If I use 6 feature maps I will get, but these are only low level features, that means one step from the pixels. I have to get the high level features. I perform another filters, another set of 6 filters or 10 filters, okay, to get the next level of features. But if I keep applying filters like that, the dimension of the feature maps become more and more, okay, and then the number of filters I want to apply at different locations also, the computational complexity in applying filters is also high, because each convolution operation here, if you want to do convolution with a filter, where I have to place this filter? At all pixels I have to place, is it not? So, if it is 100 cross 100, 100 cross 100 into those many operations I have to do for a single filter. If it is 5 cross 5 filter, 5 cross 5 into 100 cross 100, those many operations I have to do for just getting one convolution output. So, I have to reduce somehow the computational complexity without compromising the requirement I have. So, one layer, another layer that convolution neural network has is compactly representing this information in terms of pooling layer. Okay, pool the information. How should I pool? Put the maximum value in this block to the next layer, let us leave the other things, okay, that is referred to as max pooling, or put the average value for each block and then go like that, okay, that is average pooling. So, essentially it has a convolution layer followed by a pooling layer, okay, and again convolution layer because we want to extract high level features, again pooling layer, okay, this essentially is done in convolution neural network. And finally, after doing all feature extraction, I have done enough learning for filters and feature extraction. After doing whole thing, what I need one dimensional representation, because the number of classes are in one dimension, okay. So, I will take the one dimensional representation, I will do back propagation exactly in the way we have done here, okay, slightly in different manner. So, you can see here, this is the convolution neural network, it takes finally the features may be like this, okay, each filter may extract features like this, okay, one may extract horizontal, vertical and then all lines and so on, circles, all those things, okay. But this is the convolution operation. Hope you know convolution operation, I am not discussing or describing it. What we do is, this is the kernel and this is the image, wherever there is an overlap, in the overlapping region we will count how many are overlap, the overlapping region only we will multiply and add. So, the value is 1 here, it is 0 here because there is no overlap at all, these are non-zero values. So, here overlap is there, so it is value is 3, okay. So, it is like that. So, convolution operation, hope you are aware. And then some of the important things, if you want to understand, mainly those who work in this convolution neural networks want to understand the literature, you need to understand the dimensions from layer to layer how much they will be, because in papers, if you want to design your own convolution neural network, or in papers if you want to understand, there will be a table giving the convolution how many filters they use, what is the dimension of filters and so on, okay. So, from that you need to understand what is the dimension of next map. So, if you have 5 cross 5 or 6 cross 5 map here, 6 cross 6 map here, okay, if I apply a 3 cross 3 convolution, okay, I am considering such that whole convolution is within, that means I do not want to have the border effects, boundary effects, okay. So, I put the kernel completely inside. So, then what will happen, it will only start here, it will end here. So, what is the output value, output is, okay, it is 5 cross 6, so it is 3 cross 4, okay. So, essentially it is H cross W means H minus F plus 1, okay, F is the filter size, okay, H minus F plus 1 or W minus F plus 1, that is the dimensions of this, okay, that is how output dimensions are. So, you should know how to calculate output dimensions, this you can see by convolution operation, okay, calculating that. And sometimes what we do, we may not do convolution at all locations, we may take here and skip one value here and put kernel here, and again skip and put kernel here. If that is called stride, Okay, if I don't do convolution at all location, that means feature extraction I don't want to do at all locations. Okay, I want to do here, it's anyway done for this pixel now, I want to shift one pixel here and then take the feature extraction. It's not coarse feature extraction, it's okay, I sample here, features here and so on. Okay, with stride 2 and so on. In that case, stride gets divided while calculating the size. Such things you should probably understand. So this is the other thing is, see, whatever we have seen before is a 2-dimensional convolution, but usually what happens, from input image I want to extract 6 feature maps, that means 6 kernels I used, 6 feature maps I have got. Now I don't have 2-dimensional image now, I have 3-dimensional feature maps now. Okay, H cross W cross C. Now 3-dimensional feature maps too, I want to get the another 3-dimensional feature map. How do I go about? There are already H cross W cross C and I want to get another H cross, so I have it's like H cross, okay, W cross C here, okay, and from here I want to get anyway H, I will write H dash cross W dash cross C dash, I want to get, okay, another feature maps. How do I get that? Then what I do is, the operation that I do is, I perform the convolution operation with a 3-dimensional kernel now. See, I will write this, okay, if I want to get the convolution output, say assume that we have image I, which is 3 dimensions. So I is 3 dimensions, assume that. So I will write k here, okay, I is a here, okay, because I is a convolution operation you know well, I am not representing this, ik convolved with, okay, C kernel, right, k this pi, right. See what this operation I am writing it is, see I assume that I is 2-dimension H cross W cross C, where C is represented by P variable, okay, I have not represented H cross W because it is anyway 2-dimension, I am assuming that either 1-dimensional signal you write, right, usually, okay, H convolution if y equal to X convolution with H, you people may be aware of this in signals and systems, okay, we drop n for simplicity here, okay. Similar way I am dropping here spatial variables I and j, okay. So IP is the pth map, okay, of the feature map, you can see that pth map is one of the map here, okay. I am taking IP and convolving with what, kp comma l, okay, again k is also 2-dimension, okay. So if I say that this is already I is 28 cross 28, okay, cross say whatever, so 6, okay, then what I have here, P is what, 3 cross 3 filters if I am using, P is 3 cross 3 cross, okay, P is same here 6, okay, 6 I have, cross how many L I need, L equal to, say if I need 12 maps output, this is 12, okay, this is the dimension. So what essentially I am doing is, I am taking an input image, P channel of the input image, okay, and convolving with the P channel of kernel and such L kernels I have, okay, and then this I sum over P because output is only Lth map I need, okay. So this is what I do usually in this process. See, this is the mathematical notation and this is the visualization. What is happening here? This filter is 4 cross 4 cross 3, okay, 4 cross 4 cross 3 is here, okay, this is what is this, okay, this is essentially is that, okay, 4 cross 4 cross 3. How many such filters I have, how many maps I need? If I need actually output 12 maps, okay, these kind of filters, how many filters should I have? 12 filters. See, if I, instead of 3 here, if I have 5, assume that 5 channels I have before, already I have 5 channels, then what will be the dimension of this, can you tell? 4 cross 4 cross 5, because I have to start with that 4 cross 4 cross 5, and if I need 8 here, then how many times I have to do this, how many W's will be there here, W1, W2 up to W8, okay, so like that. So that's how it happens. Essentially if you want to look it as number of input, so this is I1 and then IP, okay, and then these are the input channels if you consider, and the output C1, okay, and then CL if you consider like this, then what is essentially happening? It is roughly like a fully connected neural network, okay. So each is a channel now in 2 dimensions. Okay, you can see the analogy between this operation and as well as the neural network, where each is a channel now, 2 dimensional channel. Okay, fine. So you should know essentially, if I have 6 maps to get to 12 maps, how many kernels, what is the size of the kernel? This is one more important element if you, when you design a neural network, convolutional neural network. So this is the other layer, as I mentioned. This layer, what it does, it tries to do a compact representation of the image. See what as I mentioned, there are 2 layers. One layer is convolution layer, which will do feature extraction. The second layer is what? Second layer, other layer is in convolutional neural network is what? Pooling layer. What does pooling layer does? It tries to represent the same information in a compact way. That is only its job. So if A is like this, okay, and another A is like this. So for humans we can say that both are A's. For a machine it is very difficult to say these 2 are A's, same A's. But for machine it is easy to say that these 2 are same A's. Okay. So what we do? It is unnecessary information to have at this resolution. Okay. What we do? We can do a downsampling or pooling, okay, or averaging, and represent in a compact way. That is done in another layer. So these 2 layers one after the other, go one after the other. So in a convolutional neural network, I will just skip the small details. Here, see, this is a typical example of a convolutional neural network, where we can apply the convolutional neural network for digit classification. This is referred to as LeNet model, okay, those who might have known before. So this is a very simple LeNet 5 model, where this is the digit is represented in 28 cross 28 image. Digit means 5, 6, whatever, or 28 cross 28 image. That image we will pass on 6 filters we use, 5 cross 5 or 3 cross 3 filters. Here 5 cross 5 filters. If I use 5 cross 5 filter with 28 cross 28 image, what is the output dimension size? 28 minus 5 plus 1. Okay, that will be equal to 24 cross 24. That is what we have. And again we have 6 channels because 6 filters I have used. And after that, okay, we have actually downsampling, because each channel, if I downsample, how many will the number of channels change? If I have 6 channels, I downsample them again corresponding to the corresponding channels. Will the number of channels change? They does not change. So I have 6 channels compactly represented in 12 cross 12 now. I apply again 5 cross 5 filter here. If I apply 5 cross 5 filter, what is the next dimension? 12 minus 5 plus 1, that is 8 cross 8. Okay, again I apply compact representation representing in 8 cross 8 to 4 cross 4, and 4 cross 4, 12 channels I have, I vectorize. So 192 cross 1, that I will connect to output 10 neurons. Okay, this is a simple architecture how a convolutional neural network looks. Okay, so you can see that we will skip the details, some of the details. One of the important thing to know is how do I initialize these filters. See, as what did we mention, these filters, how do I see how many filters are there? Here 6 filters are there giving 6 maps. From here to here there are 6 maps here, and then 12 maps here. How many filters are required? How many 5 cross 5 filters are required? 5 cross 5, 6 maps here and then 12 here. 5 cross 5 into 6 into 12. Okay. So essentially 5 cross 5, if I look at 72 are required. Okay. But if I require 5 cross 6, only 12 are required. Okay. So those many filters are required. How do I get those filters all length? I have to initialize something, right, with these filters. How do I know these filters? By learning. That means I have an error here, I try to back propagate and learn these filter values itself now. Okay, 2 dimensional W's I try to learn now, not just 1 dimensional W's we have done in a feed-forward neural network. Okay. So how do I do that? With some initialization and back propagation later for learning. How do I initialize? Usually we initialize by random initialization. So usually there are some guidelines, because the initialization also plays an important role. See, you are looking at the j function or cost function not in 1 or 2 variables. Okay, as we have seen in this example itself, 10 power 6 variables, million variables. So that obviously will become non-convex, okay, and it is very difficult to track where the local minima, global minima, anything of it. Okay, we can't visualize at all. So that much higher dimensional space, we want to find some good W, okay, with all elements of W. which is best suits for classification. So we have to initialize also properly. So initialization is done through random initialization, but however there are some guidelines for it. What is the range we should consider, negative to positive and so on. Okay, what is the range and so on. So usually there are some Xavier initialization and so on, which will tell that minus 1 by something to plus 1 by something, minus small positive to small negative to small positive. In that range we initialize. After that we need to back propagate. So we have already discussed this. You have seen, right, how 6 maps to 12 maps, if you want to get how many filters are required. Okay, so these many filters are required, each of 5 cross 5. Okay, 5 cross 5 required for 6 maps, 6 of them for getting 1 map here, like that. Okay, again for the next one, like that. So this is the expression that exactly I have written there. Okay, so except that the variable z is here and then some other variable there. Okay, so now the question is the error. After this you have the error here. How do we back propagate? That is the next question. How do we back propagate the error? We will see a little bit. I will not get into the details again, but I will give you an idea. And this is exactly in the same way as we have done before. If you understand in a neural network how does the back propagation happens, understanding in convolutional neural networks is not difficult. See, error you have here. So error, if you have, first find the gradient here, okay, O minus t or whatever. After find the gradient here and so on. If you have a convolutional neural network, if I want to update this weight element, okay, then what should I do? If I use my previous principle, what should I get? If I want to update this weight matrix here, what should I have? The forward process is convolution, okay. So some other process may be there for convolution, but the weight update here depends upon error here, whatever I get up to here, and the input values here, that's all. Okay, so if I want to update this, input value x into something will come, error here. Okay, same operation also happens here, but the major changes are, because you are going forward with convolution operation, you back propagation, it turns out to be correlation operation. Okay, so if you are moving through a activation function f, same f dash will come in the back propagation. Wherever you are doing downsampling in the back propagation, what will happen? If you are going in the forward direction by downsampling, if you want to bring the errors to the back, I have to do upsampling, that's all. Okay, so with these small inputs, you can see that the error gets back propagated. Wherever forward downsampling is there, I do upsampling. Okay, wherever the convolution is there, I do correlation, that's all, nothing else. Okay, so there are some, if you want to get real inputs or key inputs on how convolution here becomes correlation there, okay, you have to wet yourself with a little bit of small examples. Okay, you can take in 2 dimension, okay, do convolution operation, get output, get the errors and see how does the errors get back propagated. Try to see forward relationship and then try to see the reverse relationships and then try to see, okay, how do you write this compactly. This finally compactly is written as I mentioned like this. Okay, in the forward direction convolution means reverse direction back correlation, that's all. Okay, so it's not too difficult to see, but you have to see with small examples if you want to see. Okay, similarly it happens even for the weight update. Okay, so finally as I mentioned, if you want to update the weight, you have to see the errors in the output and the input, that's all. Okay, at any layer if you want to update the weights, what you have to see, errors up to corresponding output and inputs. But you can't multiply here because forward operation is convolution, you have to do some other 2-dimensional operation which is correlation here. Okay, flip of convolution is correlation. Okay, so something like that. So this is regarding the convolution neural networks. I will show small examples and then conclude in 5 minutes. So here you can see what kind of filters does it learn. You can see that actually, so this learns at different layers, different versions of 7, okay, and try to put it and then based on it does classification. So the kernels always we can't make much note of it, okay, but sometimes with some different way of visualization, the feature maps gives a better understanding of what's happening. It's not very easy to get the intuition on what exactly filters, are they edge filters, are they corner filters and all, but in some cases we can get. And the other thing that you can see is, even with if you train with a 3500 neurons, a feed forward neural network, you may get a maximum of 93% accuracy for digit classification on 60,000 samples and 10,000 samples for testing. But if you train a convolution neural network of 5 layers, as I mentioned now, okay, we can easily get a accuracy above 96% with the same data. So, because as you have seen, we are not bringing 2-dimensional samples to 1 dimension, we are effect of shift, writing, all these things are taken care well, and learning is happening not just for the from the features, but also for the features to some extent. Okay. So, there are some examples that students have done. So, this is one example, where they have applied for white blood cell and red blood cell segmentation and classification. So, initially segmentation is done. Segmentation can be done through image processing applications. These are the white blood cells with stain, okay, and these are the red blood cells. Now, if you see, actually we want to learn a convolution neural network, give all the white blood cells and we want to put a malignant and benign class, okay, cancerous cells and non-cancerous cells. So, what do? We want to give some input. See, should we give directly the blood cell as the input, or do we want to give some little bit of better enhanced handcrafted features as input? It is up to us. So, they have one of the student has extracted some handcrafted features and gave them as inputs. So, the kind of inputs are now we consider this as shallow features because we extract with a without not much layers, right. There is a deep neural network we call because there are hundreds of layers. Okay, the number of layers where we learn these filters is referred to as the number of layers for a network. Okay. So, and this is more means it is deep network. Okay. So, it is not initially we give shallow features with some pixel differencing r minus g, g minus b and so on, also with some other kind of like with stain, without stain images and so on. Some different versions of the input handcrafted features are given as input. Okay, and then there are different networks that are parallelly trained to get actually extract different information. And this is a conventional practice in convolution neural networks to extract better features. So, one network extracts some kind of features, other network other kind of features, we augment or stack all of them and finally give for computing the error at the output, and then from there the error and back propagate, learn all these things, all the three networks together. Okay. So, this has given a good improvement over the current methods of cancerous cells classification in terms of this blood cell classification. Of course, there are different ways in which the people explore in terms of in classification. See, should we use all samples? The answer may not be yes. You need not use all samples. Use very distinct samples, or you somehow have a mechanism to pick the diverse samples and give it to the network and train better. Okay, that there is a field called active learning. What they do is initially start with very small samples and try to see which are the samples which are difficult for this network to classify now, other samples, and only label them, do not label all of them. Okay, try to find out the samples which are tough for current network and label them, use those samples to train this better, okay, like that. Then with that he is able to see that even with very small 50% of the samples, we are able to get the accuracies better than all 100% samples using, and so on. So, the even computational complexity is reasonably less compared to ResNet 150 which he compared with, so and so on. So, there are some references I have put here. So, if you want to follow deep learning for computer vision or visual representations, so I would recommend Professor Fifi Lee team video lectures, Stanford. So, they are very good. So, they have given very detailed lectures starting from how to the theory and then training and many other aspects, and they also have given different other resources there in terms of the papers and which papers to look for, and which for even for projects there are some good hints there. I thank the students who have made these slides long back. Thank you. If you have any questions, you can ask now. Okay, thank you. You can ask me anytime. Anyway, you can be there here for a day. Thank you.